we now get into using Newton's second law and seeing how we can use the second law to solve specific problems. Okay, so what I want to do first is make note. Okay, we talked earlier about F equals ma, right? And F was F net, and net means the sum of all my forces. Okay, so if I can sum up all of my forces, and remember, forces are a vector quantity, okay? So I have to take direction and magnitude into account. But the sum of all the forces on my object, if they do not balance, they will produce an acceleration, all right? So F net equals ma, all right? Or another way of saying it is that the sum of all my forces is going to equal the mass times the acceleration, all right? However many forces I have, however unbalanced they are going to produce the acceleration. Now, let me introduce two special types of forces, all right? Because we're going to use these over and over and over again throughout the semester, so I want to introduce them to you up front. Let's introduce weight, okay? So this is the weight of an object. I'll put it over here. So the weight of an object, we actually use weight here in the United States. We use pounds. That is a measure of weight, but weight is actually a force, okay? A lot of people get pounds and kilograms confused, and in fact, kilograms is a unit of mass, pounds is a measure of force, all right? So weight is equal to the force of gravity, all right? And it is equal to the mass of an object times the gravitational acceleration it experiences. Now, here on Earth, g is roughly 9.81 meters per second squared. So for any object near the surface of the Earth, you can calculate its weight if you know what its mass is. All right, so we are going to use that particular concept over and over and over again. We're also going to use the concept of tension. All right, and tension, we denote that force as capital T, and this is just the force exerted through things like string, ropes, chains, anything like that. So if I have something hanging by the ceiling, hanging from the ceiling by a rope or something, then the force that is supplying the upward force counterbalancing gravity downward is going to be tension, all right? So any force that is exerted through ropes, strings, or chains, anything of that nature, all right, we will call tension. Cables, so on and so forth, all right? Now, because F net equals the sum of all the individual forces that can be acting on an object, I'm going to introduce the idea of a free body diagram, and this is a rather useful tool for analyzing all of the forces on an object. So, say for instance, let's take the case where we have a chandelier or some sort of light fixture, all right, hanging from the ceiling, and this is the light, right, and this is the floor down here, and I want to be able to determine all of the forces that are acting on this object. So instead of actually drawing it on my picture that I have here, I can use what I call a free body diagram. And a free body diagram is just a way to simplify your picture and just look at the forces that are acting on the object. So what you do is you represent your object by a dot. All right? You just represent your object by a dot. That makes the artwork very simple. Now I want to analyze what all forces are acting on my object here. Okay? What all forces are acting on my light fixture? Well, we can definitely say for sure that gravity is acting, because if I were to cut the chain or rope or whatever that's hanging the light, that the light is hanging from, if I were to cut that, it's definitely going to fall. So I can claim that the force of gravity is pulling my object downward, all right? And I know that my object is not accelerating. If my object is not accelerating, that means that there has to be another force upward. Otherwise, this would be the only force, and then my object would be accelerating downward, but it's not. So there has to be a force upward also acting on my object. And of course, that force is tension. And so now that I have my free body diagram, and by the way, this is not restricted to one dimension. I can have multiple dimensions. So let's say I had a block being pulled to the right and up, then I would supply the force to the right along the x-axis and my upward force in the upward direction. But now it's time to define my coordinate system, okay? So whenever you draw a free body diagram, you also want to define your coordinate system and what directions are positive and which directions are negative. I'm going to use the upward as positive convention here in this particular problem. And one classic question that I can ask is, what is the tension? If I know the mass of my light fixture, I can calculate the weight. How can I calculate the tension in the rope? So here's how you do it, okay? Remember that F net is equal to the sum of all your forces. Right? And what all forces are acting on our free body diagram? Well, I have tension upward and I have gravity downward. So I know that tension is going to be acting, and I know that gravity is going to be acting. And this is going to equal the overall mass times the acceleration of my light fixture. But what is the acceleration of my light fixture? If it's just hanging there, is it moving? The answer is no. If it's not moving, then it's definitely not accelerating. Now, this is different than when we toss the pen in the air, and at the height, its instantaneous velocity was 0, so it wasn't moving, but its acceleration was non-zero. Here, this object is not moving at all times. If you have an object that is not moving at all times, then it is not accelerating. So if it's not accelerating, if my acceleration is 0, then I can say that my mass times my acceleration is 0, because my acceleration is 0, mass times 0 is 0. And so now I can solve this equation for the tension. So my tension is going to equal negative Fg. But Fg is simply equal to the weight of my object. My mass times gravity, and gravity is negative 9.8 meters per second squared. And so if I take 9.8 or negative 9.8 meters per second squared, that negative sign is going to cancel out with this negative sign. And so what I'm going to get is whatever the mass of my object is times negative 9.8 meters per second squared. And these negative signs are going to cancel out. And this is essentially going to be mg. So the magnitude of the tension in a cable, if that cable is supporting an object hanging above the ground, then the force in that, or the tension, I should say, the magnitude of the tension is just going to be equal to the weight. And this is because the object is not moving. You could even have the object moving at a constant velocity, because if it's moving at a constant velocity, then the acceleration is also 0. All right? But if it's not moving at all, then the acceleration is definitely 0. Hence why this particular example works. All right? Now let's do one more example, and here we will look at an elevator. So imagine we have an elevator, and we have the tension in a cable moving upward. We have the force of gravity acting downward, and the overall acceleration of this elevator is accelerating upward. So it's moving faster and faster and faster upward. All right, so let's say the acceleration is upward. The overall acceleration is upward, and for now we'll skip on putting the numbers in. We'll just let you see it symbolically. Hopefully that'll sink in. So let's look at a person and the elevator combined. So we'll call the combined mass of the person and the elevator mass M, all right? And if I want to find out what the tension in the cable is under this particular circumstance, all right? Well, again, F net is equal to the sum of all my forces, and that is equal to MA, right? So what forces do I have? Well, if I draw a free body diagram in place of my actual elevator diagram here, I would see that my tension is acting upward, the force of gravity is acting downward, but now my force of gravity, my arrow shouldn't be quite as long as my tension, because, let me make this a little bit longer, make the point a little bit clearer, because I know my acceleration is upward, so I have a net upward force, so my upward force needs to be larger than my downward force, right? And so, the tension, let's back up. The sum of all my forces are going to be the tension plus the force of gravity, and again, I'm going to assume that upward is positive, and downward is negative, all right? And this is going to equal my mass times the acceleration. We're no longer at zero acceleration. We now have a non-zero acceleration component, all right? And so, if I want to calculate what my tension is, I can go ahead and insert the negative sign for G in for right here, and this is saying that I have a positive force of T in the upward direction and a negative force of gravity in the downward direction, and so my tension is going to be equal to whatever the overall mass times acceleration is plus the force of gravity or the weight of the elevator, all right? And we can write the weight as mg, and I can factor out my mass, and what we can see here is that the tension is equal to the mass of the elevator and all of its occupants times the sum of the overall acceleration the elevator is moving up at plus the acceleration of gravity. Now, does this make sense? Well, let's think about it. If I want to yank something up really fast, that's going to cause a large acceleration, and that means that whatever medium, be it a rope or a cable or a chain or whatever, that I'm pulling up with really quickly has to supply a very large force. So the larger A becomes, the larger T must become, and that's what's predicted by this formula. If I put in larger and larger A's, T is going to get larger and larger and larger as well. And so this formula is self-consistent. We could also look at the case where the elevator was moving downward, all right? What if the acceleration of the elevator is downward? Then how does the tension change in that case? Okay, well, according to my coordinate system here, what that is equivalent to is putting a negative sign here in front of A, and so this is going to get a negative sign, all right? And so when I add mg, when I add fg to this side, this is going to be fg minus ma, or mg minus ma, or m times g minus a. And what that means is the larger A becomes, okay, the less tension I have, all right? The larger A becomes, the less tension I'm going to have. And you can obviously, hopefully see what happens if I snap the cables. Well, then of course the tension goes to zero. And if my tension goes to zero, then what does my overall force become? It just becomes equal to the force of gravity, which is what the elevator would have if it were falling, all right? So even though we didn't plug in any numbers here, I hope that you kind of get the flavor of what we're going to be doing with Newton's second law, all right? In the next video, we'll do even more examples and we will plug in some numbers.